in this class, I will show you how to use the C code that we have produced last week, and how we can actually compile it and put it in the development board. Now, before we go to the compilation process, you need to download the STM Cube environment. Now I have sent you a link that leads to this web page, and I will show you what you should download. You should go to I will first have to find it. I will find it in Google. Download. So maybe I didn't send you the correct link, so I will send it again. You need to go to this web page, and we will download this STM Cube IDE. That's the development environment that we will use today for compiling the C code. So I will first talk a little bit, and in the meantime you can download the software. If you here go to the get software part, then get the installer for your operating system. So for example, here if you have the Windows version, you should get this part, this software, and it will download the package. It has about 600 megabytes, and then you should install it. And after installation, I will show you the next steps a little bit later when you have everything installed. Okay? So, some questions?
No, thank you.
Okay, good. So, when you will be ready, we will make use of the C code that we have actually compiled from MATLAB that we have done last week, and we will take this C code and we will go to this development environment. Now, what is important is that we first need to get the C code running. So I will very briefly repeat the steps that we have done last week, and we will see how the C code looks like. So last week we have discussed at the very end the function that was doing a filter. This was just an example because the filter is a quite simple code structure, and we have compared the speed that we get by running the C code on a PC or on MATLAB. We will also do the similar thing today, but we will do it with a little bit different code. What we will do is that we will take a look in MATLAB, and I will show you once again how to generate the code that we will then enter into the development environment. So our final product should be something similar to what you see now on screen. Now what you see is an example of the development environment. I will show you later how to work with it. And basically here you see that we have some C code. And this C code will be what is coming from MATLAB. And we will see the the comments, we will see all the headers that we have, and we will also see the C code itself. So now let's go to MATLAB, and in MATLAB we will look at the code that we have generated last week. So now this code is available for you in Moodle. That's the example that you will find in here. So I have updated the Moodle website, and now today we have 4 examples. We have done the first 2 examples during the last class, and now example 3 and example 4 is prepared for today, and we'll be working with those 2 examples. So if you have it on your PC, then open this example 2, which was the moving average filter. I will do the same on my computer with MATLAB, and this is the code that we have been working with last week, and this is the call for the function that we are actually using. And now what we will do is that I will compile this function which is doing the filter, and we will again see the C code that it will produce. Now for the time being, the type of the variables that we will have here in MATLAB will be double. So I will keep doubles for the time being, but later you will see at the very end of today's class that we will change the variable type to something else that will be processed much faster on the microcontroller. So let me just quickly repeat the steps in MATLAB Coder that we have done last week. So I will start the MATLAB Coder tool. I will need to enter the properties of the function that we want to define, so the function name, and I will do it here by just selecting the file name. So in my case it's this file. We need to define the entry function. We need to define the conversion of data types, and currently we will be doing no conversion, so here we'll have none. And now we need to define the test function that is calling my script, and that will allow me to input some numbers. So again, this is the file that is calling the function. We have discussed everything last week. We will now auto define the input types, and here you can see that all are doubles. Here the A and B, those are the filter coefficients. You can see that B is a vector of 5 elements, and the X, in my case, this is my test signal, so it's a vector of 20 samples. Now I can generate the code, and we will see the C code when this is done. So first we will check for issues. Last week we have used this to build the max function, and in the last step, when this check is completed, we will compile the C code. So the result for us right now will be the C code that we will be able to import into the development environment for the CPU. So let me finish the last step. We'll have to wait a little bit. We'll generate the code here in C language, so not C++, but C language. although the development environment can also work in C++. So let's generate the code, and we will see the C code, I hope, in few seconds. We have looked at the C code last week, so we will see that the C code will be made of some for loops, which you see over here, and that this code is not an optimal code because the main filter is here, what you see over there. This is the main filter algorithm. But for example, this was the checking if all our numbers that are defined, and this was the copying of the filter coefficients into the local copy inside of this function. So now what we could do is that we could copy this function through the clipboard, and we could paste this inside of our code. I see a question. Yes.
Professor, when I did the generation of the code in C, I got 56 line of code. You have 62. Is there any difference?
Maybe the difference is in the configuration of the compiler.
Okay.
Because
So
you can add commands. You don't need to include this check for infinite numbers, so that might be different.
Okay. Thank you.
So now let's say we have those files. We have one file. You see here, this is my function name .c, and then we have another file that is the function name here .h. Now, if you have some experience in C, you know that the .c files is the source code, and the .h file, this is the header file. And at C, it works in such a way that you will include the header file in your code. So you will include this .h file. And here in this .h file, you can see this line, for example. This defines the function with this name with those parameters, and the word extern means that it's not defined in this file, but it's defined actually here in the C file. So this header file is used as a definition of the function, but the actual code is then written here in this C file. So if we want to compile my C code, we need both files. You need the files .c and you need the file .h. Now what we will do is that I will show you the basics, how you can work actually with the development board, and then we will take a look on the development environment. So last week I told you that we will be working with this Nucleo board. I don't know if you already have the board for embedded systems with Mr. Hiski, or if you don't have it.
We agreed on meeting on Monday to receive the board because some people didn't directly order the board with the professor. So now we're meeting on Monday to receive the board.
Okay, so no one has the board yet?
Not yet, no.
That might be a problem because we should be working with the board today. But at least you should be able to compile the code without actually seeing what is it doing. So let me see. Let me explain how we can actually program the board, or what is inside on the board. I will show you this schematic. This is from the manual to the board, and I have uploaded this manual also to the Moodle site. So if you want to access those files, you'll find them on Moodle, and I have uploaded the files here. I've made a new tabs for the nuclear manuals, and this file is one of them. One of them is the manual, one of them is a schematic, and one of them is the, I don't know, it's just some general description of the CPU, I believe. So let's take a look on what we can find on the board. We will actually not need very much from it. This is the controller that we will be programming. This is the STM32 microcontroller. In order to upload the software and debug the code, it needs a debugger, and that's this part of the circuit. So if you look on the board, then this is the development board itself, and it's connected through those small tabs to the debugger. So you can use it as a whole. So this debugger plus this development board. But if for some application you need just this development board and you don't need to debug it, you can break this off. This breaks the electrical connections, and then this runs standalone, and you don't have the possibility anymore to debug or change your code. We will use this USB connector to download the code into the board, and it's at the same time the connector is used also to debug, so to read all the memory content and to write the memory content. So it's the same cable. In order to work with the board, you will need a micro USB cable. So the real board looks like this, and here is the USB connector that is used for debugging. This is the actual programming chip, and this is the microcontroller that we're working with. Now it has a second USB connector which is over there, and this can be used as a user USB connector. So if you have the proper firmware in the CPU, you can make it like a USB host. You can insert a flash drive. You can write the data to the flash drive, and so on. In this class, we will not be using this USB connector. Now we have one button. This is this blue button that can be used as a user input, and we will have 3 LEDs, and our very first task will be just to make the LEDs blink, so that we see that the program is actually running. Now you can see that here we have the LEDs. So here is what we will see. Now all those 3 are user LEDs, and they have different colors. In my example, I will use just one LED, and I will use the red one. Now a little bit later in the class, maybe in about a month or so, we will make use of those connectors here or here. Now the connectors, they interconnect the CPU pins, and you can use them, for example, on a cable. So what we will do a little bit later is that we will take, let's say, a voltmeter, or we will take a signal from the computer. We will connect it to the pins, and we will read it from the CPU with some code that we will create in Simulink. and then we will send the output that we have just calculated to some other pin. Now the CPU has many peripherals, and we will actually use just two of them. We will use an analog to digital converter. So the input that we will send from the PC to the board will be an analog signal, an analog voltage, and we will read it from the AD converter. We will then calculate the result. It will be some number, and we will output this number to the digital to analog converter. So the output will again be an analog signal. So actually this board, this CPU, will run the C code that we produce in MATLAB or in Simulink, and then it will interact with the PC, and in the PC we will have a model of our plant, and the PC will simulate the plant. Of course, if we would have two boards like this, we could run the controller on one board and the plant simulation on the other one. It would be also quite easy to do. Now let's see how we can actually connect the board to the computer, and how we can actually program it. So what I will do now is that I will open the STM-Cube environment, and I will show you step by step how to actually create the project. And those steps will be similar to the ones you will do with Mr. Hiski in embedded systems. So if we launch the STM-Cube IDE, it will first ask me to the directory that I want to use as a workplace. So in this directory, that's where I will have the compiled projects. It doesn't really matter where you place it. It's just a folder that you have in your computer, and in this folder you have your data. Now I will launch the IDE, and we should see some wizard that will allow us to produce the new project. Now if you open it for the very first time, you will actually not see this window as I see it here, but you should see something like this. If I open the new project, then I'll takes a few seconds to actually open it, and I will have a choice in different CPUs. So I will be able to select different CPU families. Now it's taking a little bit longer than I expected. I probably have to wait anyway. And then I will need to select the correct CPU. So now let's just wait until it opens. I will try again. It downloaded something, probably some update, and now I need to wait before this update is completed. And I hope we will be able to see the window quite soon. Well, let me go briefly back to MATLAB before it actually is doing something, and let me explain you in a little bit more detail what this code is doing. Now the filter algorithm is nothing else that if you take the sample which here is this X, and this is an array of, so this is the array X, and this is the index that you are actually accessing. And the filter algorithm is nothing else than you take this sample and you multiply it with the filter coefficient. Now in my example that you see on screen, this filter is actually very simple. We have all the coefficients, all the b's here are equal. So if I look now in my results in MATLAB here, now those coefficients that you see here, the b are all equals, and a is equal to 1. So if I see here in MATLAB that it's multiplying with this this coefficient, then I could easily replace this with some constant number. So if you know in advance what your filter coefficients are, and if they are all the same, you can do this. But this is more like a universal way how to write it. You have the array B, which is for your coefficients, and then you have your samples here in the array X. Now, in my case, the filter has 5 coefficients. So this is this 5 in this loop, and the number of samples that I have in the memory is 20. So for this reason, this is running up to 21, because it starts from 0 and counts until we have 20. Now in normal C, you would not do it like this. In normal C, and by normal C I mean C for an embedded system, you would definitely not do it like you see here, because this is what's creating a local copy of the coefficients. So here you have the input array, which you see is an array of doubles. So those are the filter coefficients, and here the code creates a local copy. So if you want to speed up your code, you can rewrite it so that here you are using directly the b's from the inputs, so this variable, and then you don't need to create at all this local copy of the coefficients. Now the reason why MATLAB is doing this is that it's a more general way, and but if you want to optimize the code, you can easily remove this from the C code. So in my C code that you will see compiled a little bit later, I will have just this for cycle, and I will keep the local copies. I will not have the local copies. I will use directly the numbers that we have here available as the inputs to the function. Now let's see if this is already finished. Okay, now it's working. So in your case, when you first launch your IDE, then you will see this window, a new project, and here in the part number you need to enter the part number for our microcontroller. So it's 767ZI. That's the type of the microcontroller. And now if I select the code, here I select the CPU, we can read a little bit here what can it do. So what are the peripherals, what is approximately the price of the CPU, and so on and so on. And we can create a new project. So if I do this, now in my case it will directly open me this new project window. In your case it will start downloading the support packages for this family of microcontrollers. So that's the second file that it will download. This file is quite large. I believe it has something like 1.2 gigabytes, but it contains all the libraries and all the examples for the CPU. So if you don't have it yet installed, then just watch what am I doing, and after you have it, you can try it, and it will certainly work for you as well. So let's select the new project name. I will just make some tests. So let's call it test, just like that. We can select what is the target language, if C or C++. I will work always with C, and that's basically all. We can select what we want as the output. So we want an executable file, which is a binary file that is uploaded into the microcontroller. We could use a library that's useful when you are producing some functions for someone, and you can then give them the compiled code, but you don't need to give them the source code, so the source C files. Okay, I think we can hit finish. Now it's gonna do something. It's taking a little while, and it will open us a different window where we will actually be able to configure the CPU. So we will be able to configure the inputs. We can configure the peripherals such as AD converters. We can configure the speed, the USBs, and so on and so on. Now this will be a compiler that this will be a window that will be graphical. Just switch to that perspective. That hold on, it's somehow slow today on my computer. So I will probably not go through the tool because it's not really the point of this subject. You will do this configuration tool with Mr. Hiskey. But what will happen is this tool will generate the C code for you. So at the end, what you will get is a file like this. You can see here that we have some project that we have just created or downloaded from somewhere. And here in the core and source directory, we have the main function. And the main function in C is always the function that starts at the beginning of your code. And if you look through this, now all this is automatically generated. It initializes the hardware. That's, for example, this function. It will initialize the system clock, which is, for example, this function. And here in this part where you see the while loop, this is actually the part where you will be writing your own code. So you see here this user code begins here, and this user end is finished in there. So if you generate an empty project, it will be exactly the same like you see here, except those two lines that I have now on my screen. And now those two lines are used to work with the LED on the board. Now if we want to control the LED on the board, we actually need to look in the description of the board, where is it connected. So here you can see that we have those three LEDs, and I found in the description that one of them is controlled with port B, It's this part, and it's connected to pin 14. So what this code will do is that this function is the library function that's available in all the files that you download as well. And this function is toggling a pin. So toggling means that if the pin was 0, then it will be 1, and if it was 1, it will be 0. So this will turn on or turn off the LED. And then there is this function on the line below, delay, and the number is the delay in milliseconds. How long will it take? So this will run in an endless loop. It will toggle the LED, wait for half a second, and then toggle it again. And in my examples, I will use those two lines to show you that it's really running on my hardware and that my code is working. Now, you don't need to create all these files by yourself. I have made it ready in Moodle. So if you go to MATLAB Embedded Coder, this tab in Moodle, then here you can find the examples for the Nucleo board. And here are the 4 folders for zip files which contain the complete project for the environment. So if you just download any of them, then you should be able to see exactly what I see here on my screen. Now the example that I was showing right now is this first one, this Blink file. And this Blink file is nothing else than the auto-generated code with those 2 edit lines that will do the blinking with the LED. Now let me compile the project. You can do it by going to the project menu and by selecting build project. And now here in the console window, we should be able to see the results. It's a bit hard to see. So let me just switch to different colors. So I will just select the white color. Something like this will be probably easier to see. So after compiling the code, here I see that there are no errors, no warnings, and now I'm actually able to upload everything to my board. So on my computer, I have the board in front of me. So let's take a look how it looks like. Now I'm not sure if the screen is frozen for some reason. I probably need to connect and disconnect my camera because it looks like there is some problem with the USB connection. So let me just do it. And let's see if we are able to see something. No, unfortunately the picture has frozen for some reason. Thinking how we could actually do it. Okay, I can compile the code right now. So compile the project, and now I can hit this button that will debug the code. So now what is happening is that the IDE gets in connection with the development board and downloads the code. And here you can actually see that it stopped at this line. You can see this this symbol, and this is telling me where it's actually waiting for my commands. So now this is already running on the development board. I can step through the code manually. You can see here we have step into step over mode. So I will just press F6 on my keyboard, and I will run the functions one by one. So we don't need to look in detail on those init functions. I will just go directly to this toggle function. Now if you look on this picture right now, the LED, the red LED is off, and if I make one step here over this function that you see here, the red LED will turn on like that. So now I have seen on the camera window that the red LED is on. Now I will do this function the whole delay, and it will wait half a second. And since this is an endless loop, it will go back to this function. Now this LED is on, so if I run this line, it will turn it off. So let's try it, and now you see the LED is off. If I run it very quickly with this button, this resume button, it will run the code automatically, and now in here you can see that the red LED is blinking. Now, for example, if I want to change the speed of this blinking, I need to stop the code, this terminate button. I can change this number. So let's say I will make it 1000. So now it will be having a half frequency. I can compile the project again, and I can debug and upload the code into my board. So now what will happen is that we see that this board is still running the code with the original frequency. Now if I debug the code, it will jump to the beginning of the program. Now the red LED is off, it's waiting for my commands. And here if I run it, then now you see that we have half frequency of what we had before. So now I'm free to write any code that I want in my C file here, and what we will do is that we will use those two lines in every example to see that the board is actually running. So now let's take a look on some more complicated example. And what we will do is that we will take the filter example from MATLAB, and we will insert it into this IDE, and we will actually run it. So we need the C code here that we have in MATLAB. So we need this file .c, and we need this file .h. Now what I will do is I will actually not take the files right now from MATLAB, because I have already prepared everything that is required. And I will open the file that you can find in my materials on Moodle. So here it's this zip file that you can find on Moodle. This is the entire project that is doing the same algorithm that like last week we have done in MATLAB, and it's generated automatically by MATLAB compiler. So let me just open this example. You can download it from Moodle. I will open my project that I have prepared, and it is moving average filter. And now I am able to import that into my environment. So here now I have the two projects. This is my Blink project, and this is my moving average project. It has a similar structure. Again, here in the core and source folder, we have the main file. I'll explain that in a minute. But here you can also note that I have some other C file, and this is actually the C file that is produced from MATLAB. So what I have done is that here in MATLAB compiler I generated the code, then I finished the generation in MATLAB, and here you can see that here in this example here we have this structure in the folder. So now this CodeGen structure is what was generated from MATLAB, and the only thing I've done is that I have taken this file, this C and this H file, and I copied them as files into my folder with my project, nothing else. So this is the file that was generated from MATLAB. So here you can see that it was auto-generated by Subversion. In fact, I have generated this code last year. So here you can see all the data related to the generation of the project. And here you can see the algorithm is the same function that we have seen in MATLAB. You can see that here I had probably a different settings of the compiler, because I did not include the checking for the infinite numbers, but I did include a check if the coefficients are 0 or if they are larger than 1. But anyway, this algorithm, this part is exactly the same like we have seen in MATLAB. So this is the actual filter algorithm, and what is actually here, that depends on the settings of your compiler. Now I have kept this as well. I have kept this local copy for the coefficients of the filter. We could modify this, but I just want to keep this right now because this should be the original file that we have from MATLAB. So this is the C file. Here you can see that this is my function name, and those are my parameters. So if I will now call this function, I need to provide the filter coefficients, and I need to provide the data, the samples. So filter coefficients will be B and A, and here this X will be my input signal, and the Y will be my output signal. So now let's go to the main function here. Again, almost all this is auto-generated, and you can see that I have added the line here in the user code includes. So here I have included the H file, the header file that was produced by MATLAB. You can find it here in the INC folder. So in my directory structure, I have taken the C file, copied that to the source folder, src, and I have taken this H file and copied that to the INC folder. Now it's a good idea to maintain the structure like this, because then it allows you to have an easy orientation in the code.
Professor, I downloaded the file, this 7.6 moving average filter, and in my source file, I don't have the my filter
Yeah.
.c folder, so I need to manually do it myself, right? Or is it, or it should be there?
Let me see the structure. So this is the zip file that you will be able to download.
Yes.
And in the core, you should have those three folders: INC, source, and startup. And if you in the source, here this is the C function.
Okay, I can't find it in mine. Okay.
You can find it.
No, I find all the other file except the my filter.
And did you download the moving average zip file?
Yes, I did. And when I opened, I couldn't see your like screen, but I opened the new, then STM project from an existing STM32Cube. Then I opened the directory where it should be.
Let me try it. So I will do it now. So moving average filter, I will download it somewhere. So let me download it, for example, in here. And this is my zip file, core folder, source, and I have it there.
Okay.
So how can it be that you don't have it?
No.
If I just downloaded the file.
Again, I'll download it again. Okay.
I don't know what's the problem, but maybe check if you're downloading the correct file.
Okay, I'll check.
So here we have one file, that's the C file, and here in the INC, this is my H file. That's basically basically this H file that we have from MATLAB.
Okay.
Now we can look in the IDE in the H file, which is this file, and here we need to change something. Now if you generate it directly from MATLAB, then it will have those two lines included, and we don't need them. Those two lines, what they are doing is that they are adding some additional H files for the compilation, and this generates additional variable types that we have in MATLAB. We don't need that right now, and this is doing the same thing for my specific function. We don't need that as well. So here you can see that I have commented those two lines. Now if you do not comment those two lines, you would need to include those two files as well in your folders. You can see here that I don't have them in my structure, but if I go to MATLAB, then I will have them here in MATLAB. So MATLAB produces those files, you can use them, but I personally see no point in using them right now because it will just occupy some memory. So therefore in my project those two files are not included. That's this file .h, and there was the file with this .h. Maybe I can open the files, and you can see that right now it's absolutely useless for us. It defines data types. For example, if you have an apple, if you have 64 bits integers, and so on and so on. So for this reason, I have commented those two lines in C. And now let us take a look on this main function. So here we are including the algorithm that we have in the C file. Now all the rest is the same, and here we see that this is new. Now what this is doing is that here I'm defining the filter coefficient. You can see that here all data types that I'm actually using, that's in floats. We will see what effect this will have later in the memory. You can see here the filter coefficients. Now I have defined that all my coefficients are the same. So 0.2, 0.2, and so on. And I have defined that the coefficient A equals to 1. Now this array A, now this is my input signal. Now in a real application, it will not work like this. In a real application, you will have one input sample, and then you will have some memory that remembers the previous input samples. Because I have used this array, I will be able to show you how the filter algorithm works without having a real input signal on the AD converter. So what my code will do is that I will take this sample one by one in a loop, and I will run the filter on the sample. I will calculate the output signal, which will be Y here, and then I will do this step again for another sample. So it's always done sample by sample. In fact, in MATLAB, we have done a very similar thing. If you actually run this code, this filter is doing nothing else than it taking the input sample, applying the filter, it remembers the history, and this is your output. Now the difference between MATLAB and C code is that this will work with the whole array, and you will just call it once. But if you do this in an embedded environment, it will always run sample by sample. So at the end, what we will have is an output signal. And the output signal will be then stored in this variable y. Now, for no reason at all, I have chosen 20 samples for input signal and 20 samples for output signal. It's just not to occupy too much memory. But actually, this microcontroller has a lot of available memory, so this does not need to be 20, it could be 2000, for example. You can see here how much memory do we actually have available with this code. I have the memory for data 512 kilobytes, and right now I have 510.27 kilobytes free. So actually in the CPU I have a lot of memory that is available. So those lines from here to there, that's what I have actually added to my code. I forgot here to move my window. So here you can see in this bottom part, you can see the size that your code is occupying. Okay, so let's move further in the main code. Now all this is the same, it's again auto-generated, and here we see that I have added only those lines. So this is what we have just seen a few minutes ago. This is the toggling of the LED on the board. So this is a kind of a live signal, and I will see that this actually is toggling the LED and that my hardware is working. It will blink the LED. And this is the call for my function. So this is the function name. This are the filter coefficients. This is the input signal, and here this is my output signal. So this C file is generated automatically from MATLAB with no changes at all. This H file is generated from MATLAB as well, but here only those two lines are commented out. And then I can simply call my function like this in my C code. So let me compile the project. This is going to take a little bit longer to compile, but it will be just a few seconds. And we're done. We have no errors, no warnings. And now we can run this actually on the hardware. So again, we will debug the code. Now this will upload the code to the board. Now let me again magnify my window with the board, and we see that the LED is not blinking because here it waits for our command. I can step through the code. Now I am at the function that I have created here. So if I run the code now, it will calculate the filter. Let's do it right now. It's stored in the memory. Right now we don't see the result. I'll show you in a second how to actually see it. And here we will toggle the LED. Now the red LED is on, and we'll wait half a second, and then we're back again at square one, and we will basically repeat this over and over. So now this actually runs my code. Now, for example, if you want to measure how long does it take to complete this function, it would be very easy to do. What you could do is that you can insert here some line, and you can say turn on the LED, then call the function, and then turn off the LED. And what will this do is that it will give you a signal that you can capture, for example, on an oscilloscope, and you can see how long does it take to calculate this function. So we can exactly time how long does it take. Now, since we don't have an access to oscilloscope, well, I have, but at home you cannot try it. We will not do it, but this will be definitely very fast since it's running on the board itself. Now let's take a look on how we can actually see the input signal and the output signal. Now we can see that if I hover the mouse above my variable, now we can see the window here, and in this window you can see the content of my array. So I can magnify it a little bit like this. I'll hover it again, and here you can see that this is the X array. This is my input signal that we have. So we have the first sample 0.2, second sample minus 0.09, and so on. And if we actually see here on the beginning, that's exactly those samples that I have used as the input. We can of course see the output as well. So again, if I hover above here at Y, now you can see here that this is my output signal. This is already what's being calculated by the filter algorithm. But if we start from scratch, if I now stop my code and debug it again, then we will be able to see that initially all the y's are at 0. So now if I just scroll here to y, you can see that here all the y's here are zeros. And we can also enter the variable name that we are looking for here in this window, and we can see what is the content. So if I now select it and right click, we can add it to the watch window here with the watch expression, and I'm looking for the expression y. So now you can see that here in the right hand corner I can open now the variable, and I see that we have all the zeros. Now if I go through my code, that nothing happens, and here when I have this function for the filter, if I run it, we'll see that here we will have the result numbers available. So let's do it like that, and here you see now highlighted in yellow that something has changed, and now those are my new numbers. Now you can try it yourself. If you enter exactly the same numbers in MATLAB in this code, then you should have exactly the same result here in MATLAB or in C language. The only difference might be at the last decimal places, because the C code runs with type float, but MATLAB runs with type double, which the type double has more decimal places available. But on the other hand, it's taking double the memory, so it will give you more accurate results, but it will consume more memory space. So what we've just done is that we have successfully debugged the code, and we are able now to run it on the development board. Do you have some questions right now?
No, it's fine.
Okay, so here is a comparison of the results that we have in MATLAB. I have actually run the code with the same input signal. So here this is the beginning of the samples, and here this is the result that we will obtain from the Nucleo board, and you can see that we have the same numbers. So for the first sample in MATLAB we had 0.0407. Here we have the same. Here the difference is that in MATLAB, in this window, you see only a limited number of decimal places. Here you see more decimal places. But it does not mean that MATLAB is less accurate. Here it's just a visual thing that not all the decimals are displayed. Okay, so let me show you another example how we can actually use MATLAB to produce some code. Now this example will again be a filter, but it will be a different kind of filter. Now this kind of filter is called an FIR filter. FIR filter stands for finite impulse response. If you remember something from the classes of, let's say, automatic control, then you have learned about the transient response. And you have learned that the transient response is a description about what is the reaction of the system on a step on its input. Probably you didn't hear about the impulse response. The impulse response is quite similar. The impulse response is that you have a system, you apply an impulse on the input, and you are watching for the reaction of the system. So it's a kind of transient function, very simplified speaking. And here this FIR filter means that the response of this kind of filter to the impulse function is finite. It means that after some given number of samples, there will be again 0 on the input. So the way it works is that if you have a system that let's say this is your system, this is your input X, and this is your output Y, then on the input you have the signal that looks like this. Here you have time, and here you have amplitude, and this should be a straight line, so it should be like this. So this is an impulse of 0 length, or 0 width, and infinite height. And here on the output you are watching for what's happening. So here if you have t, and here if you have y, and you will see something like this, and then there will be some reaction basically. And for an FIR filter it's finite, so here when your input signal is 0, after a specific number of samples, here your output signal will be 0 as well. It may sound complicated, but mathematically it's quite simple. Mathematically it is this formula, and you can see that it's nothing else than a sum. So it's basically the same equation like we have seen for the last filter. It's some coefficient b, that's this bi, and those are the samples that we have somewhere in the memory. And here this y, this is my output signal. So it's a formula that looks like this. Now the only difference between the FIR filter and the moving average filter right now is the value of those coefficients b. Now remember that in my moving average filter, all my coefficients, where do I have them? I have them in C. All my coefficients here were the same numbers. But for an FIR filter, you actually need to calculate the values of those coefficients. We will not do it, but what we will do is that we will use a MATLAB function for us that will calculate those coefficients. If you want to represent this in a graphical way, it looks like this. Here you have the current input sample at time n, and here you have the current output sample at time n. Now z minus 1, that's moving the sample one step into the history. So if you look here in this equation, what is it doing? Here we have B0 times the current sample, so B0 times the current sample, and plus B1 times the sample n minus 1, so this is here, plus the other terms. You can have as many terms in the equation as you want. And the result is the sum of all those products. So you take the coefficients b, you keep a history of your samples, and then you have the output calculated by this simple equation. Now, we will not go through the design of the filter, but I will show you the frequency response of this filter. Now in MATLAB you can plot the both diagram, which is the amplitude versus frequency, or you can plot the phase diagram here, phase versus frequency. Now here you can see that this kind of filter that I have just designed acts as a low pass filter. So all the frequencies that are below a certain frequency, like you can see here, in my case it was something like 10 to the power of minus 1 hertz, so low frequencies are here. So now those low frequencies are passing through, they are not attenuated, and here as the frequencies are getting higher and higher, now it attenuates more and more the frequencies. Now note that typically the frequency here is in logarithmic scale, and here in my case the magnitude is linear, but it could be logarithmic as well. So low frequencies are not attenuated and high frequencies are attenuated. So this is a low pass filter. Now if you look on the signal as a function of time, you will see something like this. This was my original signal that we will run in a minute in MATLAB and then in C. So I have just taken some random signal, and here you can see some noise. I have taken, for no reason at all, I have taken about 4,000 samples. So this is the input to the filter. This is the X that you have here on the filter. And after the filter, now this is my filtered signal. And this is my filtered signal as well. So here I want to show you that I can use both approaches in order to obtain the filtered signal. And by both, I mean that this filtered signal is obtained from the original signal by applying it to the whole sampled signal. So this was already stored in a memory. And here by sample implementation, I mean that I took one sample, I applied the filter, then I took another sample and I applied the filter again, and so on and so on. So this was running in a loop, and it was taking the signal sample by sample. So in MATLAB, you typically work with the signals that you have here, like this. You have an array that you have already in the memory, and then you can apply the filter on it. But in an embedded system, you take the sample from the AD converter, you apply the filter, you output the signal, and you wait for another sample. But here you can see that both results are the same. So it doesn't matter whichever you apply. It depends on your actual application. Now this is again available for you in Moodle as FIR example _1. I will just run the code right now, and we will see what is it doing. So it's this example FIR filter float. The reason for this name is that right now it's using the float variable, and the example number 4 is the same code, but it's using something that's called fixed point, and I'll explain that when the time comes. So let's open the example. Now I will not go through this entire code. What is it doing? You can do it yourself. But basically, it's loading some signal from some file. It is adding a noise to the file, to the signal. And now I'm using two approaches. Now in here, what I'm doing is that I am calling the filter that is prepared by MathWorks directly. I am applying the filter, and this part of my code is my filter algorithm by myself. It's doing the same thing, but it's doing it one by one. So actually, if you run it in MATLAB, it's faster to run the function that is ready. If you run it on some hardware, then you need to code it like this, because you need a sample by sample implementation. And now this is just the plots that will show us the result. So let's see what is the outcome in MATLAB. And it's visible here on this chart. So now this is the original signal. It's just some signal where I have added some noise. Now this is time, but actually it's not time, it's a number of sample. And this is the amplitude, again just a number. And this is the filtered signal as filtered by MATLAB. And this is the sample by sample implementation done with the for loop. You can see that the signal is the same, you get exactly the same result. In MATLAB there might be a speed difference, this will be faster, and this in for loop will be slower because it's not optimized as they have it directly in the MATLAB function. But the point here is that now I am calling this function. That's a function that I have written. It's an M file, and here you can see how it works. So this is the filter algorithm itself. You can see I take the coefficient type times this is the history for my filter, and here I call the variable pp, and here I insert in the first position of my filter, I insert the latest sample. So this is very simple algorithm. And here what I'm doing again in a for loop is that I'm shifting back the memory that I use as a history. So this is not an optimal implementation, but it's quite easy to understand that here we have those two for loops. And now what we can do is that we can compile this function and we can create a C code from this function. Now I will not do it, but I have already done that, and I will just show you the result. And the result looks as follows. Here you can actually download it again from the Moodle site, and this is my C code that was well, I will probably show you the C code in C, because here I forgot to change the comments from Czech to English, but I have it on the Moodle, and let me just open it as a project. So I will open my directory and I will open this float, project. I will close all this and I will open the C file, main C. That's the code, and now I'm using this this function. Aha! I see now. I forgot to change the comments as well. So what is different? The difference is that if you generate the code, it will generate you this, and you can actually see that here it's creating a local copy of the variable b, the same a local copy of the variable pp, which is used as the buffer for memory. It's possible to use it like this. So this is directly the code that was generated originally from MATLAB. Now, if you have already done something in C, you maybe remember something that's called a pointer. And the reason why we can use it here is that if you use a pointer in C like that, then you don't need to create a local copy of your variables. So here you can see b and pp, but you simply say that this is pointing to somewhere. You can see here that the code is exactly the same. Here I don't have any differences. Maybe the colors are different, but that's just a graphical problem. But here this main algorithm is exactly the same, and the difference is that if you use this approach with a pointer, it's much faster, because when it enters here in this function, it does not need to create the local copy. So for this reason, in my C code, I have actually modified this for using pointers. Then you need to call it in a little bit different way in C, which you see here on the screen. And again, this will be my main function. Here, in a real application, I would read a sample. And again, I think I have translated this in my code. Yes. So here in the Moodle project that you can download, this is already translated into English. So this is where I actually call my function that I have compiled in MATLAB. And now in a real application, here you would read a sample from the analog to digital converter. Here you would carry out the filter algorithm, and here you would output this just calculated sample to a digital to analog converter. Since we will be using an array that is predefined with some signals, we will run it on the board, but we will not use the AD or DI converter. And again, those two lines are there just to show that it's alive and that it will toggle the LED. So what we have generated from MATLAB, we have this file. This is my function. It is generated from MATLAB. You can see here those stars are what I have modified in C in order to work with the pointers. Now the remaining of the algorithm is exactly the same. And when I have generated that from MATLAB, I got this C file, and I got this H file. So this is the header file for the function. Again, slightly modified with this star and with this star. for the pointer. And then what I've done is that here I have included my H file, and here I have some definition of signals. So I have chosen that the filter length, so the number of coefficients, is 13. This basically allows you to tune your frequency response. Basically, what is happening if you are changing the length of the filter is that you are changing here how good the filter is, how good is it able to filter out the low and high frequencies. On the other hand, if you select a very long filter, so with very high number of coefficients, so basically if this n will be a large number, then you need to perform a large number of calculations, and you may be limited with the sampling frequency that you actually need for your application. So again, for no reason at all, I have chosen 13 as a good number. You can choose whatever you want in your application. Now, those coefficients, this array, this is actually generated from MATLAB. So those coefficients you see now we have different numbers, but if this would be the moving average filter, now all those numbers would be the same. So those numbers they actually come from the MATLAB function, which is here in this example. Here this variable b, if I now plot the b variable, you can see that it's actually those numbers, minus 0.0205 and so on. So if I now go here, you can see that it's actually those numbers. Now this is just a variable used for the filter buffer. Now in order to make it simple, I did not define any real input signal, but I have defined that all the input signal equals to 1. So all my input samples are the same. And here this is a variable that stores the output sample. So with all this, we can now run the code. So let's try it. Let's just build the project. Now we can watch here the memory window to see how much memory we actually will have available. You can see that we still have a lot of memory available. Now we can debug the code. Now this downloaded the code into the board, and now I can skip here all those functions. I can just run them, and if I want to wait just before this function, I can just double click here the line, and you see this dot. It's called a breakpoint, and if I run now the code, it will halt automatically on this line. So now if I run the code, it runs all that was there and waits for me at this position. So now what I will do is that I will add this yout variable into the watch window, and we will see the result here. This is my sample. Now initially it is 0. If I run it, it will change to some value because it will take the input sample, apply the filter, and calculate me the output. So let's do it. and now we see that this would be my first sample of my output signal. And in order to show you that it's really now running on the hardware, then again let's take a look on the development board. And here it will toggle the LED, and now the red LED should be on. And I can again step through the function. You can see that now this is calculating the output signal. We have some response, and that my red LED is working, so I can see that it's really running on my board. Now let's compare the results that we have from MATLAB and that we have from the C code. So if we do this, of course we could record this in some array, and what we should get is exactly the same signal like we have here. There will maybe be a slight difference, because here again MATLAB is running in doubles, so the numbers will be maybe a little bit different, but basically we'll have the same signal from MATLAB and from the IDE as well. Are there any questions? Okay, no questions. So let me show you the last example. And the last example will be exactly the same algorithm. It will be also an FRI filter. But this time we will not use the floats as the numbers, but we will use something that's called a fixed point number. Now, what does it mean? If you look on this code here, now I have defined that my variables are floats. Here we can see it as well. It's a float type. Now, normally the C code will work with floats, and it will occupy 4 bytes of memory. And if you want to work with floats, your microcontroller needs to have special hardware that is able to operate with floats. Now, not all microcontrollers have this unit. Well, this one does have it, but if you are concerned of let's say with price of your device, then most likely your microcontroller will not be able to work with floats. Now in C you still will be able to use them, but the problem will be that if you compile such a code, it will be very slow, and the speed difference will be something like 1000. So if your CPU has support for floats, and there is basically no speed decrease if you use them compared to integers. Well, there is, but not that large. But if your microcontroller does not have support for floats, and if you still use them, your program will be, let's say, 1000 times slower. On the other hand, if you look here on the floats, we have decimal numbers. We have 0.0 and then something. So you can work with very accurate numbers. But for many applications, such as was the filter application, you actually don't need so high accuracy, but you are looking for speed. you want that your algorithm runs at a specific sampling frequency, and it may not be possible to achieve this sampling frequency also by the fixed point numbers, by floats. Now, if you know something about binary numbers, the typical binary number looks like this. You have ones and zeros. So, for example, you have the number 0, 0, 0, 1 in binary, which in decimal is 1. Or you may have a number that's for example 0, 1, 1, 1 in binary, and this is 7 in decimal. But now note that here in normal binary code we are not able to express decimal numbers. So for example, I cannot express a number that is here we have 1, and let's say here we would have 2, so 0, 0, 1 and 0 in binary, and this is 2 in decimal, but I cannot write that it's 0.5 in decimal. It's not possible, because it's either 1 or it's 2, nothing in between. So if you work with pure binary numbers, you can only work with integer numbers, which of course will reduce your accuracy. But there is a trick how you can actually improve your accuracy, and this is called fixed point numbers. What this means is that you take the binary number like this. For example, if you have an 8-bit number, and you assign that your decimal point is here, it's a fixed position. All those numbers that are on the right are the fraction, and all those numbers on the left are the integer part. Eventually this might be the sign bit, so you may express positive and negative numbers as well. So here this is the integer part, this is the fractional part, and this is a sign bit. Now the beauty of fixed point numbers is that this is always at the defined position. Now since here we have the fractional part, we may express decimal numbers as well, but we are still occupying 8 bits. You can note here that we have a limited accuracy, because here those powers of 2 will give us only a limited ability to describe a number. So for example, by using this format, I can write that my number is 1.5. If I would have a 1 here and a 1 here, and then 0, 0 and 0. I could do the same if for example, I want to write 1.25, then it would be 1 here, 0, 1, 0 and 0. But I can not write that it's 1.2, for example. So here 1.2 it's not possible to express, because here we will see that we don't have the decimal places that are actually available. Now, why do we use those fixed point numbers? Now the reason is simple. If you use a fixed point number like this, what you can do is that you can work with those numbers as with integers, but you know that this is the fractional part and this is the integer part. The algorithm will be exactly the same, as you will see, but we need to remember for us that this will give us the decimal point, and this will be the integer part, and this will be the fractional part. Let me show you what I mean what I mean by this. Now what I will do is that I will create also an FIR filter, but I will create it with integer coefficients. So we will see that there will be a difference in the magnitude response because we will have less accurate numbers that are available. But on the other hand, as you will see later, this code will be significantly faster because it will run with integers, and it will also occupy less memory because it will work not with floats, but it will work with integers. So let me see here, let me show you an example for MATLAB. And this is actually the example number 4 that here you have at FIR fixed point. So we can download it and you can run it yourself. I will do it. So I will just move to my folder over here, and I will run this example. Now it's a very similar example to the ones that we have just seen with floats. What is it doing is that it's designing the filter by using MATLAB functions. And here I am actually able to select the number of bits that I will use in my calculations. So I have chosen that I will have an 8-bit sample, and I will have an 8-bit sample on the input as well. Now if we run this code, it will design the filter, and it will basically give me again those coefficients for it. So I will again have here this B array. But now this B array will not look like this. As you see here, we have the B function. But now the B, well, actually here I'm comparing the two filters together. So here this is the result. And here I will have the magnitude response. You can see here that this is again a low pass filter. Now here in this chart it's shown as a normalized frequency, and it's with relation to the sampling frequency. But here this will be the part that will pass through the filter, and here this will be blocked, and it will attenuate higher frequencies. To show you the significance of it, let's take a look on this picture. Here we have the original signal, which is a sine function, sine wave, with some added noise. So if I zoom this in, you will see here that I have added some noise into the sine function, and the output signal is then shown here. This is the output from the filter, and you can see that this is a nice looking function. Now the reason why here we have something 10 times to the power of 7 is here in this magnitude, and this actually means that my filter is also amplifying the signal by about 110 decibels, which is quite a large amplification. So for this reason here we have a different amplitude. But we can see that it filters very nicely the signal from the noise. We can see here an effect on the beginning, and this is related to the initial conditions that we have in the filter. Now initially, if you run it, then your initial condition is 0, so all the history is 0. And here we can see what happens when the history starts to be filled sample by sample. And since in my example the length of the filter is relatively large, I have designed the filter length to be I don't know, but it will be something like maybe 50 to 100 samples, so something like this, maybe 80 samples long. So here it's still where the history is filling, and here we have let's call it steady state, and here we have a nice sine wave on the output. So this is a transient response when the algorithm starts to work and we need to fill the history with the newest sample. Now if we want to use this code, what we can do is that we can again compile this function. This is the same function that we have been running for the last example. So let's just see it. You can see it's doing exactly the same thing. Here I am calculating the filter. It's some coefficient times the history, and it is still the same result, same function. So if I now calculate this and compile this, we will get a filter, but right now we have integer coefficients. So what this means is that my numbers that I will enter into the signal, into the filter, will not be floats, but they will be integers. Again, you can download the code in Moodle. It's this one, fixed point. And you will see that there will be basically no difference at all between the code that we have here and between the code that we have here in the fixed point example. There will be only one difference in the numbers here in the types and in the types of the variables that we will be using in the code. So let's see how the code looks like. So I will just open it, and we will see what are the effects. By the way, let's remember this number. I will note it because we should see a difference in the memory consumption, and especially we will see also the difference in speed, which we would be able to detect on the oscilloscope. So let's open this example. I will again close all my previous projects, and I will just open this fixed point example. Now this is the function created from MATLAB, and now note that here in my function I suddenly have integers. So in MATLAB I have defined that this will be integers. In the previous we had floats, so this is different. Otherwise I'm still using pointers because it's more efficient than copying the variables. But the algorithm, you can see, is exactly the same. And here, if I look in the main function, I now will include the filter algorithm And in order to give you the real signal on the output, I have included that in the file that's called test signal. Now if we look here in the test signal, we will see that this is nothing else than a defined array, and here are my samples. So again, this is taken directly from MATLAB, and it's some signal that I have generated. In the MATLAB code, you should be able to run the algorithm with exactly the same numbers, and you should get exactly the same result, as I will show you a little bit later. So this is my test signal. You can see now that it's quite long. I have generated the signal with 1000 samples, and all this would be stored in the memory. So here this would occupy 1000 bytes. Now if this would be floats, it would occupy 4000 bytes, because every float takes 4 bytes. So this will be, in floats, this would be 4 times longer. And well, in this case it's not a problem, but in this case it will fit in the memory. But if you have some smaller microcontroller, it may not be possible to fit all this into the memory. So this is my test signal. Now here I have included the filter coefficients, and the filter coefficients are also included in the H file. The reason for this is that you can generate this filter coefficients also from MATLAB. So this array, or those numbers, are again generated from MATLAB. Now, again, for no reason at all, I have chosen the length of the filter to be 100 samples. This is quite a long filter, but I want to show you the effects of this long number. And if we would have an oscilloscope, you would be able to see the impact on speed versus the filter length. Okay, so let's see the code. Here I have the main function, and now in this case it is done by the sample by sample implementation. So it means that here I take the simulated test signal sample by sample, I run the filter, and I store the output also in a variable. So now we will be able to see the input signal, which is here the array test signal, and here we will see the output signal as a variable. We will see it in the watch window, and we will be able to compare the results with the results that we have from MATLAB. So let's compile the project. It's going to take a while, well, a few seconds maybe. Now note here we have a different memory available. Previously with the floats we had 510 kilobytes. Now we have 501. The reason is the test signal. So the reason is that here I have used 10,000 1000 samples for the test signal, and here I have defined also the Y signal to be an array of the same length. So this memory consumption is larger, but it's due to the fact that I am using large arrays on the inputs, on the history, and on the output as well. And again, here we have the toggling of the LED, so we'll see it that it's running really on the board. Let's debug the code. So now it will upload everything into the into the board, and we should be able to see it on the board. So let's just magnify it. I will again insert, let's say, breakpoint over there, run it, and now it's waiting here. Here we can see the array of y's. Initially, all is initialized to 0. And if I now will step through the code, we will see that this will fill sample by sample, and it will fill the array with the results. So let's see it. Here now we will see the first sample here will be calculated. Because we are at the beginning, then it's possible that this will be zeros, because we still have the history 0 and our current signal did not reach yet this output position. So let's step further, and now you can see that here we are filling slowly the memory sample by sample. And if I now open it, here we have so far few samples from my signal. So we have 10 samples here from 0 to 9. And you can see that all this is integer numbers. What this means is that here now we're working with integers and not with floats. So this will be much faster than floats. And now if I just enter the breakpoint here at this position, oh no, I forgot, I pressed the wrong button, so I need to do it again. I will just run the code until the part we are toggling the LED, which is right now. So right now we have all the memory that is filled with the results. If we look here, we have all the numbers that all the signal is processed. And now if I toggle the LED, we should see it that now it will turn on. So it's really running on the hardware. And if I remove the breakpoint and I will run it, we can see that the LED is blinking, and here the frequency is given still by this delay, the half a second delay, and this is actually quite fast. Now let's compare the results that we have from MATLAB and from the C code. So I have done it here. So this is the C code that we are actually running. This is from MATLAB, and this is from the C code. Now note that there is a difference. The reason for the difference is quite simple. Here in MATLAB, what you can see in MATLAB, now those are floats, and those are integers. The numbers may look different, but if you actually plot this signal, it will be the same signal, but it will just be scaled. So the trick here is that by using fixed point here in C, although I don't get the same numerical results, I will get a scaled signal. The signal will be the same but scaled as in MATLAB, but this code would run significantly faster because it's in integers as compared to the floats. So I suggest you to try all this by yourself, to run here this codes on the boards, or at least compile them if you don't have the boards. And when you get the boards, then you can upload the code, and you can see with the board how is it working. Do you have some questions?
It's clear.
Okay, great.